Hi everyone, my name is Grigoris Velegkas, and today I will present a new model of sharing information. This is joint work with my advisor, Yang Tsai. As we know, we live in a world that's becoming increasingly more complex. Fortunately, there are a lot of data out there that can help us make more informed decisions. However, these data are not immediately available to the agents who need them. Hence, there have been created markets that sell information. For example, consider a bank which has to decide whether it will approve a customer's loan application or not. The bank might have some prior knowledge about the borrower, but this is an important decision to make, so it might be willing to pay in order to get more information about the customer. Thus, there have been created services like Equifax that provide their customers with extra information about individual borrowers. Other examples include navigation and the traffic. Of course, many drivers might have an idea about how the traffic looks like in certain routes they follow. However, since the congestion levels are constantly changing, they are willing to use extra information about the current state. Why is it an application which provides such a service? The main topic of this talk will be the seller's problem of finding the revenue optimal way to reveal information. In order to analyze this program mathematically, we adopt a model recently introduced by Bergman et al. In this model, the uncertainty is captured by a set of states of the world. The buyer has to take an action, and based on the action and the state, she receives a payoff. We denote the states by omega, the actions by A, and the payoffs by U sub omega comma A. The knowledge that the buyer has is captured by prior distribution over the states. We call this prior distribution her type. The buyer can choose to get some extra information from the seller and pay some price for it. As in the auction setting, we assume that the type is drawn according to some distribution, which is known to the seller. Now, the seller reveals information by sending signals that are correlated with the state of the world. You can think of the signaling scheme that the seller uses as tests. Based on the results of the test, the buyer might either choose to deviate to different action from the one she was thinking of taking, or stick to the same one. We call the signaling schemes experiments. In order to come up with the optimal menu of experiments, we first have to consider how the agents evaluate the extra information they get. Suppose that someone has concerns about being exposed to COVID-19 and is given the option to take a test. Naturally, in this setting, there are two states of the world. Either the agent is sick or she is healthy. The actions that she can take are either to quarantine or go out. Based on the symptoms that she is experiencing, she has figured out the probability of her being sick. We denote this probability by theta. This is her prior knowledge. Now, the results of the test are correlated with her current state, but they're not 100% accurate. You can think that the first signal means that the result of the test was positive, and the second signal that the result of the test was negative. We assume that the test has a 30% false negativity and 30% false positivity rate. Once the agent receives a signal, she performs a Bayesian update and forms a posterior distribution. We can see here the posterior distribution that the agent forms when she receives one of the two signals. The red line represents her posterior probability of being sick after she receives signal 1 as a function of her prior. Similarly for the blue line and signal 2. Now, based on these posteriors, she picks the best action for her. In our example, we see that when she doesn't receive any information and theta is greater than 0.5, she will choose to stay home. If she receives the third signal, she will choose to stay home only if her type is greater than 0.3. On the other hand, if she receives the second signal, she will opt to stay indoors if theta is greater than 0.7. It's also easy to compute the probability that each of the two signals is sent. Now, the value of an experiment is simply her expected payoff after she receives a signal from that experiment. Note that the max operator allows the agent to map its signal to some different action. Now observe that different types can map the same signal to different action. This will be important later on. So for our example, let's see how the valuation function looks like. we see that even in this fairly simple setting, the evaluation of the agent isn't linear in her type. You can see that it's just a piecewise linear function, and this is caused by the max operator that we discussed before. Now, returning to the general model, we assume that the seller can offer different experiments to different types and price them accordingly. There are many companies that are offering such subscription models. For example, Oracle ID tracks some firm's customers across several devices and documents the data that this firm has with behavioral observations from multiple sources. Now, the timeline of the interaction between the buyer and the seller is the following. First, the seller commits to a collection of experiments and prices, which we call a menu. We denote this menu by M. Also, we denote the probability that the seller sends a signal K when the state of the world is omega by pi sub omega comma K. Then, the state of the world and the type are realized. Based on her type, the buyer selects the experiment she prefers and pays the corresponding price for it. As in the auction setting, we assume that the buyer is quasi-linear. After that, the seller draws a signal from the predefined distribution and sends it to the buyer. In her turn, the buyer performs a Bayesian update in the way we described before and picks the action that maximizes her expected payoff based on her ex-post distribution. Finally, she receives the corresponding payoff based on the state and the action that she took. I want to point out a crucial difference between selling information and selling items. Consider the simplest auction setting where the seller wants to sell a single item to a single buyer. Assume that the seller has fixed the probability that she gives the item to the buyer. Then, the value of the buyer for this lottery is linear in her private type. One thing that we can immediately notice from the example we discussed before is that even in the single-dimensional environment, where we have just two states and we fix some experiment, the value of the agent for that experiment is not linear in her private type. Because of the fact that different types interpret the same signal in a different way, the value is now a piecewise linear function. This shows that this model is more complex and presents more challenges when we try to derive algorithms and characterization of the optimal menu. For example, Bergman et al. Proved that even when there are only two states, the seller needs to use randomization to maximize her revenue. We can now see an overview of our results. In the single agent setting, we saw that the tractability of the problem depends heavily on the way the input is specified. We focus on three different input scenarios. When everything is given explicitly, we prove that the problem can be captured by a polynomial-sized linear program. We then show that in the case where the input is provided implicitly, but we have accessed the best response oracle, we can still get an additive f betas, assuming that the number of states is constant. Finally, in the implicit model, where we don't have access to that oracle, we saw that it is NP hard to get a constant factor approximation of the optimal revenue. Now, the original model by Bergman et al. Only deals with a single buyer. We propose an extension of that model for the multi-agent setting, and we saw that the problem is still tractable when the input is provided explicitly. We will elaborate more on the different input models later. We start with the single agent setting. In the explicit single agent model, we assume that the type distribution as well as the payoff matrix are part of the input. Bergman et al. Showed that the outcome of every menu can be captured by a responsive menu. Now, responsive menu is one in which the buyer submits her type and the seller picks the best experiment for her. Moreover, that experiment has the property that the signals are direct action recommendations, and it's in the best interest of the type to follow the recommendation. This result allows us to capture the optimal menu using a polynomial-sized linear program. Our approach is inspired by Chen et al. Here, we can see the linear program that captures the optimal menu. This linear program might look familiar to many of you because it resembles the one in the auction setting. We have three sets of variables. The first set is the prices we charge. The second set is the experiments we use. And the last set consists of some helper variables. I will describe how we use them soon. Let's now look at the constraints. The last two sets are simply the feasibility constraints. The important difference between the LP that's used in auctions lies in the OEC constraints. Recall that in our setting, the value for the experiment isn't linear in the buyer's type. This means that some type theta might consider misreporting as theta prime and then mapping the recommendation of the signal to different action. This creates a phenomenon that we call double deviations. Note that the responsiveness of a menu only guarantees that the type is obedient to the recommendations when she reports truthfully. If she wants to evaluate how much she likes the experiment of some other type theta prime, she might have to use a different mapping from recommendations to actions. This phenomenon vastly complicates the IC constraints. We use the helper variables z sub I of theta comma theta prime to help us capture the value for signal I when theta misreports as theta prime and uses the best mapping for that specific signal. Another minor difference compared to auctions is that the IR constraints state that the net payoff of the buyer from buying information has to be at least G of theta and not 0. This is because even without receiving any information from the seller, the buyer still takes some action based only on her posterior distribution and receives some payoff for it. We now turn our attention to the implicit model. In that model, we assume that the distribution of the types is given along with access to the best response oracle. Now, the best response oracle takes as input the distribution over the states and returns the best action with respect to that distribution. An example that this model applies to is navigation under traffic. Assume that we want to travel from the source to the sink in our example graph, and the edge weights depend on the state of the world. In this setting, the action set consists of all the possible paths from the source to the sink, which is exponentially big in the natural description length of our problem. Nevertheless, the best response oracle can be implemented polynomially using our favorite shortest path algorithm. The main issue is that now the number of actions can be very big, so we cannot apply the previous algorithm, since the size of the linear program that we use depends polynomially on the number of actions. The gist of our approach is the following. We start by merging signals of the optimal menu that are close in TV distance and come up with a menu that only recommends actions from a much smaller action set. Now, by merging signals, we mean that we merge the columns of an experiment matrix, so that if we start with a very fat one, we end up with a much thinner one. The number of columns is now polynomial in 1 over epsilon, where epsilon is the amount of revenue that we're willing to give up. The new experiment only recommends actions from a set A prime. Moreover, we saw that this set can be computed by querying the best response oracle polynomially many times. This menu generates a negligible amount of revenue less than the optimal one. We then saw that the optimal menu, which recommends actions only from the set A prime, can be captured by using a slightly modified version of the linear program that we saw before. In order to do that, we saw that M prime is a feasible point of the polytope, and every feasible point corresponds to a menu. Thus, the output that the LP generates gives us at least as much revenue as M prime. Our previous approach depends heavily on the existence of a best response oracle. We need the best response oracle in order to compute the reduced action set. When we don't have access to that oracle, we can create an instance in which getting a 1/2 approximation of the optimal revenue is NP hard. Since we have a very limited characterization of the optimal menu, we focus on the simplest case possible. We have just 2 states of the world, 2 actions, and a single type. Bergman et al. Proved that in this setting, the optimal menu consists only of 1 experiment, and this is to exactly reveal the state of the world. Nevertheless, we saw that if we can approximate the optimal price by a factor better than 1/2, then we can essentially solve the satisfiability problem. We now shift our attention to the multi-agent environment. When we try to extend the basic model by Bergman et al. To a multi-agent environment, there are many modeling decisions that we need to make. In auction, the seller has a limited amount of resources that she can distribute, so there is naturally competition among the agents who try to get them. However, when one is selling information, there is no such barrier. Naturally, we have to consider whether the agents are competitors or not. The case where the agents are not competing to get extra information is trivial. This is because the sellers can consider everyone separately and use the approaches that we described before in order to come up with a revenue optimal way to sell information to each one of them. We now turn our attention to the setting where the agents are competitors. This setting is much more interesting. There are many ways we can model that competition. For example, one could say that the payoff of each agent depends not only on her action and the state of the world, but also on the actions of her competitors. This isn't the route we follow here. We have instead chosen to restrict the number of agents that the seller can send extra information to. More precisely, we assume that the seller can select only one of the agents and send her a signal. We're not yet done with the modeling assumptions that we have to make. There are many ways that the seller and the buyers can interact. The amount of information that is exchanged through that interaction affects the IC constraints and the privacy of their types. The first step of the interaction is for the seller to commit to a mechanism and to announce it to the buyers. In this environment, having just a menu isn't sufficient to maximize the revenue. Once that happens, we need to decide how the buyers submit their types and how the seller submits information to them. Reveals information to them, sorry. There are three different ways this can happen. The first way is for the buyers to submit their types publicly. The second way is to have them report privately and reveal both the signal and the experiment from which the signal is drawn from to the winner. The last one is when they submit the types privately, and the winner only gets to know the signal. It is not very hard to see that the first option reveals the most amount of information to the agents about their competitors' types, and the third one the least. Now let's focus on the IC constraints. Assume that the bidder wants to misreport. The difference between being truthful with or without seeing the bids of your opponents has also been studied in auctions. In the former case, we have a DSIC mechanism, and in the latter case, a BIC mechanism. The IC constraints of a BIC mechanism are less stringent than the IC constraints of a DSIC mechanism. This is because when the agent tries to strategize, she has less information available to her. In our case, though, there is also the phenomenon of double deviations, which isn't present in auctions. If a buyer doesn't know the bids of her competitors and the experiment that the signal is drawn from, she has the least amount of information available to her when she considers the best deviation from the recommendation of the signal. So, in this case, the model has even less stringent IC constraints than in the previous two. This means that it can generate the most amount of revenue to the seller. For these reasons, we stick to that model in our work. All in all, the interaction between the buyers and the seller proceeds as follows. Firstly, the seller commits to a mechanism and reveals it to the buyers. Once that happens, all the types are realized. The buyers send their types privately to the seller. After that, the seller selects a winner with some probability that depends on the type profile. Moving on, the state of the world is realized and the seller sends a signal to the winner, but doesn't reveal the exact experiment that the signal came from. Finally, all the types choose an action and receive some payoff for it. It isn't very hard to prove that the optimal mechanism can be again captured by a linear program. The problem is that this program has constraints and variables that are exponentially big in the number of agents. In order to circumvent this obstacle, we leverage the reduced form approach that has also been used extensively in the mechanism design literature. Before I conclude, I want to briefly mention some other extensions of the original model that we can handle. So far, we have assumed that all the types have the same payoff. We can extend our results to the case where the buyer's type is her prior as well as her payoff matrix. Another extension we can handle is the setting in which the types distribution, as well as the priors that the seller has access to, contains a small amount of noise. In that case, we can construct a menu that achieves revenue which is epsilon close to the optimal one. Finally, I want to quickly point out some future research directions that would be interesting. Now, in the implicit model for a single agent, we have assumed that the number of states is constant in order to come up with an F betas. If we want to get rid of these assumption, we have to use a different approach than the one we have in our paper. When we have at least three states, we have empirically observed that the optimal menu is complex. A natural question to ask is whether a simple menu can approximate the revenue of the optimal one in this complex environment. Now, turning our attention to the multi-agent setting, we have already discussed about different models one can consider. It's not clear whether we can design the revenue optimal menu using our approach for the other models. Thank you very much for your attention. I would be very happy to take any questions you may have during the live session.